We're back. Let us discuss the homework. Who has done something? I hope you at least tried to draw the pictures. And I will then explain why I find it interesting to draw the pictures. Who has drawn the pictures and who has made the calculations? You did it. Okay. Can you show us what you have, or it's complicated? Let me just a second.
Give me a minute and I'll continue.
Do you have it on computer? Then I
No.
No.
Not yet.
I will then just a second. I don't. Yeah, I want to announce you as a co-host, but I have problems with this.
I think I'm already the host because you left, and so I'm already.
I see. Wonderful.
Okay, so I'm not sure about the last part 5 of the question. I found some numbers, but it doesn't fit with the numbers that were said. But yeah, we'll see.
It doesn't have to.
Oh, okay. Okay, can you see my screen?
Yes. You can make it large. Wonderful. Like this. Okay, now explain. We will discuss.
So for problem 1, we had to draw the different configurations for different number of segments. So for segments n, so when there's n equals 1 segment, there's only 4 different possibilities with 4 different arrangements. And then with n equals 2, it becomes 4 squared because it's 4 to the n. And that's still counting that segments can fold back on themselves. And then for n equals 3, it becomes 4 cubed. So I didn't draw them all. They said that you can stop at a quarter of the number of possibilities. So I didn't do all of them.
Okay. But first, what you can do is to understand that you have a 4-fold symmetry. So the total number of configurations is 4 times the number of configurations in which the first segment is showing up. And then you can draw all of them, essentially.
Yeah. And this is what I did. You can see here, these 4, the first segment is showing up.
Yes.
And then these 4, the segment is showing to the right. Sorry.
Yes.
These 4 segments showing to the right. These 4, the segment is showing down. And then these 4, the segment is showing to the left.
Wonderful. Now let's look at the at 3 steps. What happens here?
So I started again with segments 1 and 2 showing up. So here, here, and here, and here. And then the last segment is up, right, left, down.
Correct.
Then the second group, I don't think I wasn't as rigorous after this. I just kind of did them as I could start thinking of them.
No, not all configurations here. Okay.
No, I haven't drawn all the configurations. Yeah.
even not all for the first step are. Okay, let's go on.
What do you mean, go on?
There were some following questions.
Oh, okay, the next question.
Yes.
Okay. Wait a sec, I can't remember what the questions were.
Mm-hmm.
How many configurations W can be found from model one?
Mm-hmm.
So if M is the number of degrees of freedom for each segment, W is M to the N.
Mm-hmm. Correct.
And so, but that's taking into account that these segments can fold back on themselves. But if we have a self-avoiding random walk where the segments can't go back, then there are only 3 degrees of freedom for each segment except for the first one. So then it's...
This is an approximate.
Yeah.
This is not quite correct.
Ah, okay.
Mm-hmm. Now, let me look at your, first I make a comment, and then we will continue. The comment is the following. When we look at this picture with the rhombuses on the square lattice, which show us the points which can be reached in 1, 2, 3 steps. For example, you have shown here in figure 3 the points which can be reached in 3 steps.
Yeah.
These are, let me make a comment. Can you see what I am doing here?
Just, yes.
So we have a square lattice. I will draw a square lattice. And I define on this lattice the length by the number of steps. So I start at 0. And for example, this point has distance 3. 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 They are not only the points which can be, they're not the only points which can be reached in 3 steps, but these points are the points which are the furthest, the maximal ones, which can be reached within 3 steps. This reaching in number of steps on a given lattice, in this case on a square lattice, gives me the distances on the square lattice. The distances define the matrix, and the matrix given by the number of steps is called, on a square lattice, is called the Manhattan matrix. So what I have here, these rhombuses are the circles in Manhattan matrix. This is a mathematical definition.
Okay.
Now, I simply wanted to take this word in my mouth because it's close. Now, we have to calculate the mean squared displacement, the numbers of configurations and the mean squared displacement. In the case of simple random walks, this is indeed extremely simple. And you seem to have done it. So if we go further, we can have a look. And then I can show you the trick which we will use in one of the further lectures, I think in 2 weeks.
So here we can see the different lengths, the different points that we can reach with a 3-membered chain. I wasn't sure if we had to do, I only just realized that, did we have to do n equals 2 and 1 as well, or was it just n equals 3?
Essentially n equals 2 and 1 as well.
Oh, I only did n equals 3.
If you know how to do it for n equals 3, it's already good. Okay.
So yeah, there's basically 3 different distances that can be reached. So there's so r is the distance between starting point and end point. And
Yes.
so r can equals 3, which is like this. R equals root 5, which is to these ones here. And then r equals 1, like that.
Yes.
And then I counted the number of ways you can reach these different points. So for r equals 3, I worked out there's only 4 ways to get to these end points. For r equals root 5, there are 20. There's 3 different ways per point, which you can see here, to reach that point. And then for r equals 1, there are 9 different ways, which I've drawn vaguely here. And so then just multiplying out the number, and you end up getting, if you add them all together, you get w as expected. So the number of different configurations.
Yes.
And then you just apply the formula and you get root means, is it root mean squared?
Mean square, yes.
Yeah. Mean squared end-to-end distance is 3. For the ideal chain, and for the self-excluding chain, it's 4.5 repeating.
How do you know this? How do you count? Have you counted all of them?
Yes. Yeah. So for the excluded volume, I discounted all of these ones where the chain falls back on itself. So there's only these 2 possibilities which can occur for the distance of 1.
For the distance of 1, they are indeed 2 possibilities. Just let me have a look at my figure.
So for example, it can go like this, or like this, for this to go to this point. So when for the excluded volume theory, to go from this point to this point, it can only go like this or like this, because all of the other configurations need the chain to fold back on itself, which we can't do here.
This is correct, but still I have a feeling that you somehow are not counting all the configurations here. Just let us draw them and then I will now before I will draw them, I will ask the question: has everybody else obtained the same result? Then I will not have to redraw them, because what I have now is only a feeling.
Yes, for me.
So we can compare the number of configurations in the let's say for r equal to 3 here, and we have 9 configurations in the beginning. You have 9 configurations. I mean, yes, I mean now for simple random walk, 9 configurations of no. If I look in your table, so you have 4, 24, and 36 on the total.
Yeah.
Gives me 36 plus 28, which is
64.
Yes.
36.
64.
64, correct. So all of them are here. And now
Yeah.
all the 4 with the length 3 are still there. All the from 24 of the length square root of 5, they seem all to survive. And from the 36 of length 1, when you're starting up, what do you, it means that for a single direction you have 6, and from this 6, you say only 2 survive, and these are the angles.
Yeah. Initially, for the ideal chain where it can fold back on itself, there were 9 possibilities, and I stopped counting after all of them add up to 64, because that's the number of possibilities as W, and there can't be more than W. So
this is correct.
And for the second case, I found W equals 36, and this works as well. But then you were saying that you weren't sure about my W for the self-avoiding chain.
Was not sure about your self-avoiding chain with the ones. Okay, let's try to redo it. Because first, okay, I will draw the picture once again because I wanted to show something else. So I will count 1/4 of all configurations, which means I always start with the step up. And the configuration with the end-to-end square distance 9 and with the end-to-end square distance square root of 5, they all survive. They do not fold on themselves. None of them. The ones I can start up, down. This one I can start up, left, right. I can start up, up. This is not one. I can then start up, down, up, down, up. This is one. Then I can do the 2 P's. Down. I can start up, left, and up, right, down, up, left, down. And there must be 2 more, but starting up, because you said there were 24 then. Up, what did I, okay, up, down, right, and up, down, okay, let's draw it like this, up, down, left. These are the ones. So now I have 6 ones, from which 4 are...
There's some you've forgotten now.
Huh?
There's some you've forgotten. There are 9, not 6. There's a
9. What have I forgotten?
Up, down. There's up, down, down. Oh no, you've done
okay.
Up, down, but there's up, down, up.
Down, and the whole sequence. Up,
Yeah.
down, left, right, up, down. I'll draw it like this. Left, and up, down, up. I already have. So there are 3 more.
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9. From which only 2 survive, namely these ones.
Mm-hmm.
Okay. Then you got r equal to 3. You have now, you multiply everything by 4 and sum up, and you get r squared 4.5. I got something different. Maybe I missed some configurations. Wonderful. Now, what happens if you try to fit r squared?
Let me get the. Oh, wait a sec. Let me get the thing up. Can you still see? Can you see this?
Yes.
Okay. A bit too big. So I only did it for n equals 3 because I didn't do n equals 2, and then
But
and I
it's,
didn't and I didn't really understand the hint saying to evaluate the plot to plot r squared versus log n. I just put the numbers into the calculation.
You try to plot a figure over 1 point, a line over 1 point. So what you are writing here is correct. Yeah? Now let's remove this. First, let us calculate. What happens for 2. So we are assuming, this is an assumption, yes, that r squared goes as n to the power of, you say, 2 nu, which means like this. A times n to the power of 2 nu. This means that r squared ln r squared is ln a plus 2 nu ln n. And this means that what you essentially have to do to get nu, yes, is to plot for different values of n. Logarithmic plot ln r squared as a function of ln n.
Okay.
Now I ask everybody whether this is clear, and the trick is known, that to get a power you have to plot on a double logarithmic scale.
Professor,
Yes?
even if we just substitute the value, we get that index, right? Like I didn't plot up, but I substituted.
Substituted where?
I mean, I followed the log. I took the log on the both side.
Yes,
And the A term will disappear because it's a constant.
it's a constant.
So I get that index is equal to log the log of r squared divided by log n, and the whole divided by 2. Like,
No, you didn't get an index. You got, what you say is that, so what did,
I got a formula for index.
what does mean you have a formula for index? Something like this?
Yes.
But how do you know that this equation works at all as a whatever approximation?
I didn't understand what.
You didn't understand.
Yeah.
First, have you calculated these guys, the r squared, for, so let's make here a table. R squared of 1 n equal to 1 is 1.
Yes.
What is r squared of 2?
R squared of n is equal to 2. It's I got 2.667.
Imagine that this is correct, which means that this is essentially in the normal numbers, as a quotient. This is 8/3. 8/3. And r squared, this is correct. R squared n equal to 3 is equal to, this was 4.5.
4.55.
Okay, 4.5. Let's put 4.5 here. And now this log of this is 0 and log of n is 0. And now we have to put here that this is n equal to ln2, ln3. Yes, we have to draw the points here. And then we have first to see whether they more or less lay on a straight line. This we do not know. And essentially they don't have to, because this Flory approximation is asymptotic. It's for large n. And the question is whether it works for moderate n. Now let me try to do something here in the background. Just a second. You cannot see anything because...
I think I need to stop.
Yes. Just a second. 4.5. What is 4.5? Okay, let me put here 4.5. Just a second. Here I will put just a second. 4.5. Now let me evaluate. So I will show you something. Evaluate cells. And now evaluate cells. And now evaluate cells. This is just a second. Just a second. Once again. And now I can share screen with you once again. Just a second. Where do I have my Mathematica? It's here. Now I put the numbers here, and these are the points. This is essentially what I wanted to draw. Here I have log n, and here I have log r squared. These are the numbers. So you see, they do not exactly lay on a straight line. They don't have to, because the straight line is the asymptotic behavior. And the slope is approximately 1.4. It's not 1.5 as it should be, but it's not very far. And this is essentially the exercise I wanted you to do, because this is how one gets this nu by, or at least in numerics, by counting the configurations. Now I can close it, I can stop it. And now it was not a lot, it was relatively simple, but one should be patient. The question is, are there any questions to this part? Yes.
What is the Flory? What is the Flory index?
This is exactly this r squared, the dependence of r squared of n for the case of the self-avoiding chain. So for both variants, now let me remove this and return to the discussion. for a simple chain, for a simple random walk chain, we have R squared goes essentially is A squared n. This is what we got last week. And this you see from the dimension. R squared must have the dimension of the length. The n dependence is here linear. For the self-avoiding chain, we have that this is some number prefactor, maybe slowly changing function. We will discuss this. And then you have A squared from the dimension. And then you have n to some power, which we call 2 nu. So here, this would correspond to nu equal 1/2, so to say. And here, nu is not 1/2. It's some power which is not 1/2. And we see that this 2 nu, if we define nu as the corresponding power in the dependence of R squared on n, this is larger than 1. This means that for large n, for long chains, the self-avoiding chain is the end-to-end distance in a self-avoiding chain is considerably larger than in a simple random walk. This is the first observation. Now, who can tell me why is it larger? Why does it have to be larger? And this we have seen essentially.
Is it because it can't fold back on itself? Whereas the ideal random walk is, it doesn't matter where it goes. Whereas for the chain, there are some constraints.
Correct. Try to formulate it in a slightly different words. What configurations are forbidden?
The already occupied cells.
But what does it mean?
Overlap of the chain. Or
once again, sorry, I didn't.
I mean, the configurations which are overlapping on itself, it's forbidden.
This is correct. This is the definition.
Yes.
But if you look, just look in our picture where you have these configurations which are forbidden, to what kind of distances do they correspond?
They correspond to the shorter distances.
Shorter distances. We forbid the compact configurations. So this means that the relative weight, all configurations of self-avoiding walk are also allowed for simple random walk. But those which are forbidden are disproportionately represented by the compact configurations of a simple random walk. So therefore, a self-avoiding walk is an extremely loose object, essentially. It misses the central part, so to say, of configurations to some extent. This we will see. And this was one of the reasons to give this exercise here. Was very simple. You didn't need any mathematics, but you have seen something. And another reason was to remind you on the double logarithmic plotting. And if you want to get a power law dependence to understand what power there, you have to plot on the double logarithmic scale. And what you see is essentially that your curve has a different, a slightly different exponent than what happens if you simply divide the coordinate of the last point by the y coordinate of the last point by the x coordinate of the last point. Again, so we have learned something. I wouldn't say we have learned a lot, but we have learned something. We've played a little bit with this stuff. Now, let me discuss two other things which are immediately connected with this exercise. Now, one of them is that 1 to 3 and even 4 and even 5 you can do by hand in 2D. In 3D is more complicated, but still you can do it by hand. And then it's 1 to 3 many, and when it's many you cannot do by hand. Now, in order to count the configurations, you have to keep them all in computer memory. And if you start considering configurations of a simple chain, and then you have to remove the forbidden, you have this binomial coefficient, which grows essentially exponentially. And the total number of configurations, let's say in 2D, grows as 4 to the power of n. Now, if you have n, I don't know what, you get many, which means if you have, let's say, the configurations of 20, just let me calculate. You can also calculate what is 4 to the power of 20. For example, 4 to the power of 20 is equal to 1, 3, 6, 9. It's approximately 1 billion. So this means that to keep the configurations of 20, each of them have 20, so to say, 40 bytes, you need 40 gigabytes, which means that having 25 or 30 and counting them all is practically impossible. Counting 30 is terabyte, and you want to do something with them. It's already a complicated computer problem, and you will never come to 100, let alone 1,000. So there are two possibilities. And one possibility is, I would not teach you how to do this, I simply want to make you understanding what exists. And one possibility is to try to guess the behavior of the functions, of general functions, having only a few points. If for some classes of functions, it is possible, and there is a method of so-called Padé approximants, which works quite well when you have, for example, this number of configurations from, let's say, 1 to 20, and then you do something better than simply trying to put the straight line. You try to get the corrections to this line. You try to fit it by the beta approximation. And it can be automatized, and here you then can get reasonable extrapolation. So one method is to use mathematical extrapolations from 1 to 3, maybe 20, maybe 25, then your computer is over, and then you extrapolate to very long. And you need 10 to the power of 4, let's say. And this is one variant. And another variant is indeed simulating the PDF or immediately simulating R squared. And there is again some mathematics behind it. And one of the method here is the following. You first learn how to transform the configurations. It started from essentially simulating the simple random walks. So here, do you see my lattice? Yes, one can see my lattice. Imagine you have a random walk here, and you start from some configuration of random walk. Now it's a simple random walk first. Yes? And what I can do for a simple random walk, I can use the so-called, it's a variant of bond fluctuation algorithm, or it's a king jump. This variant is a king jump algorithm. So what I do is that if I choose a point on my random walk and consider, and it's laying within the kink, this is a kink, I can mirror the kink as if it is here and here. I would have the pivots. So now I got a different configuration of the random walk, and it is also allowed. Or if here, imagine I consider this point, yes, and now I consider this kink, this configuration will go into doubled bond here. Bam, 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 bam. And if I have the end can make whatever it wants. If you want to simulate dynamics of a simple random walk, this king jump model is a very nice model, and there is again a mathematics behind it. And if you do it long enough, you sample adequately possible configurations. There are many configurations, but after you do it long enough so that each of your sites on your random walk got a possibility to jump several times, you sample the space of all random walks, the set of all random walks adequately. And behind this, there is a Markovian corresponding theory based on the theory of Markovian processes. And then if at each step you follow the end-to-end distance and average it over the time of all configurations, you get a nice approximation for the end-to-end distance. For self-avoiding walks, you can also do this when checking at each stage. You start from a self-avoiding, that your configuration is still self-avoiding. But for longer chains, most of configurations will be not self-avoiding. So you are losing computer time. You are losing it for nothing. And here on the lattice, you can use a different variant of the simulation. Now imagine this is a self-avoiding walk. And this is a pivot algorithm. So this is a self-avoiding. So I choose once again at random one of the sites, one of the places, and I declare this as a pivot, which means that now I take the whole rest of the chain, I may break the chain here, and rotate it. So I took this and I have simply rotated it around this as if this was a point of free rotation. And then I check whether the parts of the chain overlap. In this case, they do. Then I throw this configuration away, don't consider it anymore, take a whatever other point and make the same rotation here. I mean, arbitrary rotation. For example, if I take now, this is not good. And if I take this point and this part and rotate it, for example, like this, I get a self-avoiding configuration. This is now. And if I do this long enough, so I do not sample all the configurations and follow, for example, end-to-end distance, or look at some other properties, Again, one can show that it works adequately, that what I get is an adequate sampling of the probability space of all configurations of all these chains. And this is very nice, because using this and starting from a self-avoiding configuration, which you get by some other means, it doesn't have to be random. You understand? The first one doesn't have to be random. You get very nice results. And many, many years ago, it was just when I came to Germany, we needed these long chains. I think it was 91 or 92. You can imagine what computers were there at that time, and you could easily simulate 20 or 30,000 long chains using the PC at that time. It was the 386 processor. Nothing special, extremely slow by today's measures, much slower than your cell phone. So these are the methods. Yes.
Yes. So it's only possible to do this computationally. There's no mathematical formula that we can do by hand.
The answer is as follows. There is a kind of perturbation or renormalization approach. I simply say the words, I don't think you understand. Maybe you're a physicist, you may understand this.
I've done perturbation theory, yeah.
Yes. So there is an approach which is essentially a renormalization group one. It's essentially a perturbation theory, which allows you to get results for self-avoiding chains starting from a theory for Gaussian chains, for the random walk chains, which is the basis, the unperturbed system. Now, the problem there is that A, it is a complicated approach, and therefore I don't dare to talk about this in this course. One has to teach the whole mathematics beyond this renormalized perturbation theories. For physicists, it's okay, one can learn. The rest has first to learn what a perturbation theory is, and how do you draw the perturbation diagrams and so on and so forth. And then you get the approximations. And the thing is that these approximations, when you start, they are uncontrolled. You don't know how well do they work. And then you still need numerics in order to get sure that they work more or less. Then, in some cases, you can get the exact result. But essentially, the only known cases in which the results are exact are pertinent to 2 dimensions. And you normally live in 3. In 3 dimensions, the perturbation series converge faster, but they don't stop after you get something exact. You don't know where to stop. For real theoretical masochists, there is still a huge field of work. It's very interesting. I never did it because my main interests were somewhere else, but I know how to do it. And if you want to learn about this, there is a book by De Cloiseau on this. The book is as thick and complicated. If you want, we can look up. I can look up just new Fenster. De Cloiseau. No. Polymers. No. I must first look at the correct citation, sorry. Let me come back in Zoom, because somewhere here. I can find it out, but it's the Quasol. No, I must have a look. I must have a look first at citation and then find the book. So there is a whole book about how to do this, and I would say it's already complicated theoretical physics. And my aim here is not to show complicated theoretical physics, but to present the qualitative or semi-quantitative methods which are necessary to understand, not maybe to calculate, but to understand what happens in polymeric systems. I have a very modest aim, and I have very little time. So this is the statement. So in principle, it is possible. And then again, in principle, if you want, after I show how you get a diffusion equation for polymeric systems, we can discuss a little bit what happens if the systems are interacting, and then how to build first the simple perturbation theory. I wouldn't show the renormalization approach, but I am afraid that what happens is that the chemical rest of the group gets scared, and this is not my aim. Nobody has to get scared. Yes? Now, another thing we can start doing or discussing during this homework, and I will rediscuss it in one of the future lectures, is the following. So here the statement is that we are not out of power to do something theoretically, and we do something theoretically, and we can do a lot theoretically. However, we are doing uncontrolled approximations, and in order to be safe, we have to check them by simulations. And then we believe both. If we cannot check them by simulations, or if the results are different, we don't believe either. This is the second problem. There are many people who believe simulations closely. I worked with such people. I worked with people professional in molecular dynamics or professional in density functional theory. But I have some reservations still against simulations, because how do you know that they are stable, that there are no instabilities? How do you know that your result is really pertinent to the system you simulate? You believe this. Okay, now I wanted to tell something else, which is related to our work, and this is the following. Now let me draw again the lattice, and what I'm speaking about is pertinent both to the lecture and to this counting exercise, which we had as a homework. Now I have a lattice here. And essentially what I will now do is, I draw the dual lattice. My points are laying here. So these are the points of the lattice, and I have a cell around each of these lattice points. So my lattice would be when I connect the points, and I will use these cells for writing their numbers. Look. And now I will explicitly use, I will only consider simple random walks. It is not possible to extend or to simply extend this counting method to self-avoiding walks, but also using it for simple random walks gives us very important insights, especially in the cases where you have the systems with complicated boundaries. Imagine your polymer is in the pore, or sitting in a capillary, or sitting in a capillary with a, which is not simply a tube, but has, for example, a spherical part inside, or sitting between other polymers, or whatever. Imagine that it's enough for our purposes to consider a simple random walk model for this. And now let's count configurations. What we remember is this is the beginning. This is the site 0, the origin of my initial lattice, of this red lattice. Now imagine that at the first step, I could go here, right, left, up, down. And the total number of possibilities to reach each of these sides in one step is 1, 1, 1, and 1. And the rest are zeros. I simply do not write zeros in the empty cells. Now, let us look at the cell of 2 steps, at the walk of 2 steps. In order to make 2 steps, I first make 1 step and then another one. So I can make from here a step here, 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 and a step here. And then I can make from here a step here, a step here, a step here, and a step here. And the same from here. So how many ways are there, for example, to come from here to here in 2 steps? I only have to sum up this one and this one, so there will be 2. Here I will have 1, here I will have 2, here I will have 1, here I will have 2, because I can also come from here, and here I will have 4. So what I am doing here, indeed, is that in each next step, so look, now I remove the picture. And I was starting here. So I had at the beginning here 1 and 0 everywhere. Now, I put in the next here 1, 1, 1, 1. This is 1 step, and after 2 steps, I put in each cell the sum of the numbers which stood in its neighbors. 2, 4, 2, 1, 1, 2, 1, 2. And here also 1. At the third step, I put everywhere the number of the sum of what was staying in its neighbors. So for example, here, it will be 3, 3, 1, 3, 3, 1, 3, 3. So it must be 2, it must be 2. So it's 4, you see. You got it, but let's do it, because you have to erase. Or I will draw several. So now I have my lattice here. It's 1. Then it will be 0, 1, 1, 1, 1. At the next step, it will be 4, 0, 1, 0, 2, 1, 2, 0, 1, 2, 0, 1, 2, that's all. Then at the next stage, it will be 0. Here I will have 8, 8, 8, 8, and then from here I will have here 0, and here I will have 3, and so on and so forth. So at each next stage, I duplicate the table and put everywhere the sum of the numbers which was standing, so it's not 8, it's 9 here, because it was 1 here, 9, 9, here it will be 0. The sum of the numbers which was staying in the neighboring cells. And these are the number of ways which start at 0 and end in the corresponding cell. From this, I can then get the equation for the PDF and get its solution. It will be exactly the same Gaussian. But I get, using a continuous approximation of this procedure, for this procedure, I will show in the lecture then how to do it. I will get here the diffusion equation. And it's the best way to solve diffusion equations in the presence of the boundaries, in the presence of essentially absorbing boundaries or reflecting boundaries. We will need the absorbing one. And this is how people, in form of, I would say, young women sitting with these sheets of paper, were solving the diffusion equations for heat and neutron propagation in the first Soviet nuclear bomb. And the method stems essentially from Zildovich. This is the direct enumeration. And it's the best you can do. And this is computationally extremely simple. It's simpler than to seriously solve the corresponding differential equations. And I will go then the inverse procedure. I will start with this method and then get the corresponding differential equation as an approximation. So you see that starting from an extremely simple assignment, we have seen or learned, if you want, many important things. And some of them will be of use for us in what follows in the next 1.5 months. Now, I have an administrative question. And this is as follows. Are you grown up enough to do your homework without that I check it and collect them? This is the question. If yes, we will discuss everything in detail. We will discuss each problem up to everybody understands what it is about. I simply have very little time. I don't have time to control them and to read them carefully. Because, you know, all this online stuff, when I suddenly have to put the whole scripts for huge course in electrodynamics and to make all the student administration without secretary, I am the chairman of the administration of the examination board on physics and so on and so forth, the less I bother with your homeworks, the better for me, and I'm lazy. So if you are able at least to think about your homeworks, then it's okay, and I will not organize this folder where you have to upload it and whatever. If you want to send it to me and to discuss it with me, I am always accessible per email. You know my email. I'm igor.sokolov@physique-berlin.de. I'm always here. We can talk. If you say, then forget about sending me your homework or uploading your homeworks. Let's not do this. Let's discuss them like we did it now. Now the work was like this and the discussion was like this, but it will change. And let's assume you are grown up and you do this homework simply to be able to discuss with us during the next exercise hours. Now, I propose that we close and we rejoin tomorrow. Let me have a look when. At 1, quarter past 1. And we will go a little bit further with this random walk stuff and calculate first the force which is necessary to pull on the polymer, to consider what happens at small elongations, at large elongations. And then I will play with some physics behind it. And then I will play a little bit with the polymer in the pore. And for the polymer on the pore, at the beginning of next week, I will discuss the mathematical solution, which is based exactly on this, which starts exactly with this exact enumeration scheme we discussed today. Okay, are there any further questions?
Actually, yes, I have, but I would like to, like, if others wants to go, then maybe they can. Maybe I just need to talk to you because it's about lecture 2.
You can
yes.
talk to me. Everybody can. If nobody wants to listen, you can talk to me now.
Oh, okay. So in the lecture 2, I followed the PDF till I get the pressure equation. And
Yes.
afterwards, the PDF says that there is an alternate approach to get the viral expansions.
Do you think I remember what lecture 2 was? Let me try to find it. For this, I will click down. Now I will go to macro 21. No, not this one. 21, and there will be somewhere lecture 2. Now it's lecture 2. And now I can share a screen with you so that you can tell me what are you speaking about. Just a second. Once again, share screen, lecture 2. So what did you mean here and where?
Oh, my mistake. I'm so sorry. It was tutorial then, tutorial lattice gas. I'm so sorry.
What tutorial lattice gas? Let me open the tutorial lattice gas.
I'm sorry.
Can you see it or I have to stop?
Yes, I can see it.
Okay, lattice gas. Wonderful.
In the last page,
Yes.
there is an alternate approach. And we get the final entropy equation below.
What do you mean now?
Yeah, you can, like, there is an alternate approach to obtain the viral expansions, and you explain how to substitute, and we get the final equation. Right now we can see, like, the general structure.
Yes.
So I am confused in this. I'm a little bit lost. Like, constant plus the ideal system entropy plus these coefficients. The
Yes.
coefficients are okay, but I don't understand the constant and for, like, the ideal gas system entropy. Is that the equation which we obtain in the
But look,
format of?
look, if you want, look here.
Okay.
And then translate the thing to concentrations C. Now, this M phi is essentially N.
Okay.
And the term, this term, with phi ln phi, this comes from the second term, from the correction. This is this.
Okay.
And this is constant plus entropy of the ideal system. This will give you the equation for the ideal gas. This is ideal gas.
Okay.
And the rest are the corrections. And they have 1 power less than the power of phi here, because 1 m phi translates into n, which is constant.
Okay, I will think on this. Okay.
If you're talking this way, but check the the 1, 2, 3. There is a plus, minus, minus, but I think it should be plus, minus, plus in the last equation.
It might be because I was. So this guy is the cubical term, so it will be plus.
Yeah. Okay.
But it doesn't matter because no, if they're all positive, it will be plus. Yes.
And is there any chance of getting to know how the question can come in the exam about this, like derive the equation for the lattice gas model, or do
There will be no question derive the equation for the lattice gas model, but we will use the equation for lattice gas model so many times during the course that you will learn it. And we'll use all possible variants of the equation.
Okay. Thank you.
What is important, what will be important, is this expression from which we will start several times. This is the expression with two, I will have to explain it again and again, but this form of the entropy of a lattice system with two components is very important. And it will reappear and reappear with small modifications in different systems. And we have seen here how it appears in the simplest variant of such a system, which is the lattice gas. And then essentially, again, we have seen one reincarnation of this form, almost. We will see it tomorrow, because you have here a binary system again in our lattice random walk in 1D, because the total structure is the same. Simply we have taken more terms into account, which we discussed away here, because they never play a role for the entropy. Like this 2 pi, which goes into a constant, and some other terms which go into the constant, which doesn't give me anything. So this is important.
Okay. Thank you.
Okay, you're welcome. Are there further questions? If no, let's close this for today. If you want, you can talk a little bit among each other or also leave. I will stop my screen, and we meet tomorrow shortly after 1 o'clock in the afternoon and continue our discussions. Bye.
Thank you very much. Bye-bye.
Bye.
Bye.
Thank you. Bye.
Bye.
Okay, hello, we are 3 today, up to now. Can you hear me?
Yes, I can hear you.